once continuous distribution of notophagous species that have been pulled apart via the action of plate tectonics? Or was there some sort of series of jump dispersal events or some sort of sweepstakes route via dispersal that accounts for the distribution that we see today? So we basically have these two models to explain sort of these weird disjunct distributions. I'm showing you notophagous, but there are literally tens of thousands of examples we could sort of go through. This is just a little bit of a cleaner example. So one possible explanation is perhaps dispersal could account for this distribution that we see today. And the dispersal would refer to the movement of a species across a pre-existing barrier, so that this could have happened 3 or 4 million years ago when the continents were very close to their current position. We had sort of this dispersal event. Alternatively, under the idea of vicariance, we could have had an event where a barrier appeared such that a once continuous distribution was pulled apart. Okay, so at one time, South America was connected to Australia and through Antarctica, and they were all physically close together in the temperate zone. That could have been a single large area of the lineage of notophagous that over a period of about 100 million years ago pulled apart and gave us the distribution we see today. So dispersal and vicariance. So it seems simple enough on the surface, but as you drill down into particular examples involving notophagous or any other number of things, you realize that these are sort of extreme examples, and actually you can sort of have both operating simultaneously, in which you have some vicariance and you have some dispersal, allowing for both to occur. So don't think of them as strictly separate processes, that it has to be one or the other, because the two often work together a little bit. So what I'd like to do is give you an example involving the Panamanian land bridge, and we're going to focus on terrestrial mammals, but this, up until about 3 million years ago, and I should actually back up, from a period of about 200 million years ago until 3 million years ago, so for most of the last 200 million years, North America and South America were completely separate continents. There was no connection between them. And beginning about 3 million years ago, what we call the Panamanian land bridge, Panama basically came and connected North and South America for the first time in 200 years. And what happened was the creation of this land bridge effectively took a sweepstakes route and turned it into a corridor so that animals could begin moving from North America to South America and from South America to North America. Right, so this happened during an epoch called the Pliocene, which I will not ask you to remember. Paleocene, Eocene, Oligocene, Miocene, Pliocene. But this event was called the Great American Interchange. And your book refers to the Great American Interchange. I will as well. And there were these faunas on North and South America had evolved independently over this 200 million year period. And so in South America, there were all sorts of strange animals, including glyptodonts, now extinct. This is about the size of a Volkswagen bug. Okay, so a relatively large mammal, and a relative of the armadillos. We had the giant ground sloth. That's like a white-tailed deer for scale. These would get about 9 to 10 feet tall. As a matter of giant ground sloths moved from South America to North America. And there are still trees in North America that we see that have adaptations to defend themselves against giant ground sloths. If you were to go out into the woods and see a honey locust, you'll notice that there are no thorns on the lower branches, or I'm sorry, there are thorns on the lower branches, but once you get up to about 10, 11, 12 feet up in the tree, those thorns disappear. So these trees are still waiting for the giant ground sloths to come around and eat them, and they're all well defended against them. So giant ground sloths are another big one. And then finally, there were some rodents as well that are South American in origin. The capybara is the world's largest rodent. These are the size of pigs. They can get over 100 pounds in size. This is actually a small one here. But a species that we think of as a classic North American rodent, the porcupine, that lineage is actually a South American lineage that moved into North America just within the last 3 million years. There are some classic North American species, South American species that actually originated in North America and are now sort of classic South American species. So these include things like tapirs. This is a North American species that moved south 3 million years ago. Horses, llamas. Again, we sort of think of these as just sort of classic South American species that you find in the Andes and in the grasslands. These are North American camels that moved south in the last 3 million years. And then my favorite example, jaguars and the pumas, or mountain lions in South America. These originated in North America and moved south just within the last 3 million years. So there was this great American interchange of wildlife, from the south moving north, from the north moving south. Other cool animals moving from the north to the south included elephants, carnivores. So in addition to the jaguar, the bears, in South America there's a mountain bear called the speckled bear, which is North American in origin. There was a saber-toothed cat in North America that moved south. There was a South American saber-toothed marsupial cat that it ended up outcompeting very quickly, and that South American species went extinct about 2.5 million years ago, just from the pressure of having to deal with a placental saber-toothed cat. So, if you look at the number of mammal families that were found in South America prior to the Great American Interchange, there were about 32 mammalian families, which included several marsupial families, but also placental families. Towards the beginning of this interchange, the number of families of mammals went from 32 up to 39 families. And following extinction events, like we saw with the marsupial saber-toothed cat and some other weird animals, the number of mammal families in South America dropped from a high of 39 down to what we find today, which is 35. And there was a lot of replacement of South American families by North American families of mammals that basically moved during this interchange event. So, in focusing on the mammals, you're sort of probably thinking of dispersal. You're probably thinking in terms of secular migration, as these continents get together and have movement back and forth. And so, in one sense, the creation of this land bridge that connected South America and North America provided an opportunity for dispersal back and forth, providing connections between the two continents. But at the same time, that event took a once continuous biota of marine life and separated that by land. And so we ended up having a vicarious event where a once connected marine biota now became isolated on either side of Central America. So when we think about vicarious dispersal and the movement of plates, tectonic plates of continental crust, often what might look like something that is a vicarious event for a terrestrial species could be a dispersal opportunity for marine species, and vice versa. So in terms of thinking about tectonic plate activity, sort of back to this original idea, dispersal and vicariance aren't completely separate ideas. They're often linked but associated with purpose. Questions on vicariance and dispersal? Yes?
So this is only specific to marine life, like no other.
For the vicariance event associated with the closing of the Panama Bridge? In this particular case, yes. In when about 15,000 years ago, North America was connected to Asia via Alaska. The sea levels were lower, and so there was land that extended all the way from Alaska over into Asia. And so we had this land bridge, but as those sea levels rose, we took a once vicariant marine community, and that became connected once the sea levels rose, and that ocean sort of came between. So that it could go both ways. The book sort of scratches the surface on looking at species richness and latitudinal gradients. I will say, for ecologists and biogeographers, this question of latitudinal gradients and species richness has been it's attracted a lot of activity over the last 20 years or so, and it seems to only be increasing as we get more data. And for most, but not all, species that we look at, we tend to find this pattern of as you move from the temperate zones towards the equator, from the temperate zones into the tropics, you tend to see this increase in species richness. And so because this pattern occurs over and over again in amphibians, in reptiles, in vascular plants, birds, mammals, you have to stop and ask, like, what's going on? What's driving this pattern? And because the pattern was so striking and affected so many different groups of organisms, the initial thought was, well, this should be an easy problem for scientists to work out because it's just such a powerful and striking relationship. And the short, sort of the punchline, which you jump to right away, is there's still no satisfactory answer for this relationship that we observe. Sort of the short version. Your book sort of explores 4 separate hypotheses. There were about 9 hypotheses currently in vogue, and about a half dozen others that have been sort of discarded and left by the wayside. No one's pursuing those anymore since they didn't hold up over time. So there's one of the difficult things to do is when you have this kind of pattern, you get a group of scientists that say, well, we've tested this and our hypothesis is correct. You get another group of scientists that say, we have a different hypothesis and we tested it and it's correct. What do you do in those sorts of cases? So what I want to do, sort of the short answer to that is you sort of hold these as sort of competing hypotheses which are not fully resolved yet at this point. You say that both hypotheses have explanatory power. So we'll briefly run through 4 of these. And the first one we'll look at is sort of the regional energy availability hypothesis. What a terrible name for a hypothesis. If you're ever going to invent something new, don't call it the regional energy availability hypothesis. Call it something cool. Basically, what this states is at the equator, the sun's directly overhead for most of the year. The amount of energy being captured at the equator is higher per square meter than you find in the temperate zone, certainly the polar zones. And this, if you're sort of following along the logic here, it's sort of a bottom-up idea. Because there's more energy available, there's more plants capturing that energy. And because there's so much energy, there's more opportunity for just more plant biomass, which effectively creates more opportunities for more species to thrive in that environment. And because there's so many different plant species, that's going to sort of elevate the number of animal species that you can get in that environment. and so forth. Another idea is that, sort of related to this, is tropical regions basically have this favorable growing season all year long. In the tropics, there's not a winter. In parts of the tropics, there's a dry season, but during the dry season, there's still relatively high levels of productivity, especially in tropical rainforests. But in physically extreme environments, like Ohio and further north out in Canada, we might have a 6-month growing season, but we have a 6-month season that's not very favorable for life at all. In fact, conditions are so harsh here right now that a bunch of our birds that were around all summer that eat insects are like, see ya, I'm going to Central America. I'll be back in May. Right? I'd rather take my chances flying thousands of miles to get away from here than stay here through a winter.
Why even bother coming back?
Competition. But because, and the short answer there is because there are birds down in Tierra del Fuego and parts of far South America that are migrating north and sort of pushing them out as they come up. All those birds coming together, it's not going to work out. So, so the scientists who sort of advocate this particular view say if regional energy availability is an important contributor to species richness, you would expect to see a correlation between potential evapotranspiration, PET, and species richness. I know PET is one of those things you saw a long time ago with styrene. Bring it up again. Potential evapotranspiration is a sort of approximate measure of productivity in an ecosystem. And in semitext, we saw that PET, potential evapotranspiration, was in fact correlated with mammal species richness. Furthermore, mammal species richness had a stronger correlation with potential evapotranspiration than any of the other things they looked at. So suggesting, at least for mammals, this seems to be a leading hypothesis. To explain the diversity, the latitudinal gradient in mammal species richness, the regional energy availability hypothesis is a pretty good explanation. All right. Another possibility is sort of the water availability hypothesis. And this is sort of what it sounds like. In tropical regions, they end up getting a lot more precipitation. In fact, there are places in, I believe in the Congo, that get up to 16 meters of rain per year. I believe the wettest place on Earth is actually in the Hawaiian Islands. It gets also about 16, 18 meters of rain per year. But it's not unusual in parts of the tropics to be getting a meter, 2 meters, 3 meters, 4 meters of rain per year. Here, we don't get that kind of rain. We get about a meter a year in an average year. So the general idea is water availability limits species richness because all organisms ultimately require water to survive. Water is not a limited resource. And so the variable that we would use to sort of see if this hypothesis is correct, we look at total precipitation per year to see how well that correlated with plant species richness or amphibian species richness or any of our other hypotheses. All right, the net primary productivity hypothesis is the third explanation. Many of the most diverse habitats on Earth are among the most productive, which includes things like coral reefs, tropical rainforests. The idea is there's more energy to divide among more species, and we measure this using actual evapotranspiration as the variable. So we're testing for net primary productivity as a driver of latitudinal gradient in species richness. We also look at the latitudinal gradient in actual evapotranspiration, AGT. Test that. And a fourth and the final hypothesis we'll cover in this class. I'm sure you're more. If you're not, I know you're bored to death already just hearing about 3 of them. I'll give you a fourth. I promise I won't give you 8 more. The habitat diversity hypothesis is sort of predicated on this idea that tropics contain more habitat diversity. This can contribute to higher beta diversity with various elevation gradients, and we can measure habitat diversity using plant species richness. So if we're using habitat, if we're testing the habitat diversity hypothesis, we actually cannot test this with plants because plants is used as the predictor variable. But we can use this to test the habitat diversity hypothesis to try to explain the diversity of amphibians, or the diversity of reptiles, or birds, or mammals, or a subgroup of those of wasps, or butterflies. Big picture, again, there are multiple explanations for the latitude and gradient species richness. There's no unifying theory at this point, but lots of explanations that do have explanatory power. So do review that at least one more time in the text. Questions on our latitude and gradients? Yes?
So that one is not dependent on like species.
No, it depends on plant species richness. I just wanted to finish up briefly with some hopefully easier concepts to wrap your brain around. To talk about the sun, solar geometry, and seasons of climate. As you know, the sun, God bless it, sustains all of life on Earth. And the heat of the sun is basically transferred to Earth. It's 93 million miles away. It has to get here via radiation. And so as that travels across space, those waves pass through space or matter. And so when that incoming solar radiation strikes matter, such as soil or water, some of that matter is going to get some of that energy is going to get absorbed, and as a result, that matter is going to and the angle of incoming solar radiation ends up affecting the amount absorbed. So at the equator, the sun's light is coming in from directly overhead, and as a result, you get basically a great, I guess the technical term is you get a greater photon flux density per square meter, per square centimeter of land at the equator than you would at the poles, where as that light comes in, it's sort of spread out over a broader area. The key thing to keep in mind is at the equator, that energy is concentrated. So a square meter that's being heated by the sun in the tropics, it's getting more energy than we're getting here in the temperate zone. And we're getting more here in the temperate zone than we're getting up in the polar zones, because this becomes more diffuse. This becomes more diffuse for each given. The reasons for this, as you sort of move across the curved space, you get more atmospheric scattering, so the less light is reaching the surface. So this ends up resulting in differential heating of the Earth's surface. So we get more heating at the equator and less heating at the poles. We also get more heating at noon than we do at dawn and at dusk, because of the sun's position relative to the Earth at that point. So this point where the sun's rays fall perpendicularly on the Earth is known as the subsolar point. So when you have the sun's rays directly overhead, we refer to that as the subsolar point. And I've been using the equator as sort of our stand-in for the subsolar point, but that's not entirely correct. Because the Earth is tilted on its axis at 23.5 degrees, solar radiation can fall in different places depending on what particular day of the year it is. So we recently had the fall equinox, where the sun was directly over the equator. The sun is directly over the equator on every fall and every spring equinox. And what happens is, as the Earth does its circuit around the sun, we're getting close to December, coming up on the December solstice. The sun's rays on the December 21st are going to be directly over the Tropic of Capricorn, which sits at 23.5 degrees south latitude. So right now, the subsolar point is basically between the Tropic of Capricorn and the equator. It's sort of moving further south. So on December 21st or 22nd, whenever it is this year, the subsolar point will be directly over the Tropic of Capricorn. So right now we're moving into southern hemisphere, southern hemisphere spring. We're moving into southern hemisphere summer as of December 21st. So it's getting warmer and warmer in the southern hemisphere. The days are longer. Getting longer there. Alternatively, as we sort of go back around and spring comes around and as we move towards next June, the June solstice, the subsolar point is basically going to move from the Tropic of Capricorn back up to the equator on the equinox, and then on the summer solstice, the subsolar point will be directly over the Tropic of Cancer. And so that'll be the longest day of the year for us in the northern hemisphere, and we get differential heating in the northern hemisphere associated with that.
Aren't there other things that affect how strong the sun is? Like, aren't there like spots in our atmosphere that allow more sun in? Like, I know over in Australia, there's a big like hole in our ozone that makes the sun stronger.
The best way to answer that question. Those effects are trivial compared to these broader effects associated with the axial tilt. And the hole in the ozone layer effectively is filtering out light in the ultraviolet spectrum, not all the visible lights. The visible light's actually able to come through the Earth. A lot of the UV light that can cause mutations and cancer, that is what's been filtered out. And so that's what's associated with ozone. It's not making the Earth any warmer, but it is letting more harmful radiation come.
That's a good
So the last thing I'll leave you with is, does anyone know the day of the year when the Earth is closest to the sun? It's sometime in January. Yeah, it's around January 10th. So as we get closer and closer and closer to the sun, it's going to get colder and colder and colder. Climate's complicated, as I promised to go back to that at the end of the day. I think that's it. Again,